Good evening, all. Firstly, mobile phones, they're all switched off, are they? Buzzing or any other blooming things, or tweeting or whatever they do now. So, tonight, the Battersea gas main crossing, Chelsea to Battersea Pipeline tunnel project, very interesting project, and very much in the public gaze. Our four speakers: Andrew Hedgner, Project Manager for Cadent Gas. Andrew works for Cadent Gas, the UK's largest gas distribution business. Andrew is a chartered civil engineer with over 18 years of experience across the utility and wider construction industry in various engineering, design and project management positions. For the Chelsea to Battersea tunnel, Andrew is the client project manager with overall responsibility for the £17.5 million project, including feasibility, detailed design, consents, construction and commissioning. Ovi Franza, contracts manager for Barhale, responsible for the delivery of their tunnelling and heavy civil engineering works in the southern region of the UK. He has over 15 years of experience in tunnelling and has been involved in projects like Olympic Park, Crossrail, Tideway and flood alleviation schemes across London and Thames Valley. Nick McCrossan, site manager for Trio. Nick joined MacDonald in 2012 and has worked on a range of major tunnelling and transport infrastructure projects. He has worked as designer on the Northern Line Extension project and Thames Tideway East project. He is currently the design integration coordinator for High Speed 2 Phase 1 main works civils contracts. In 2017, he was seconded to the principal contractor as the site manager for the Chelsea to Battersea Pipeline project and spent a year with the team delivering the project. Veriuska Ortiz, geotechnical engineer, MacDonald, has been geotechnical engineer with over 7 years of experience working in Venezuela, Italy and the UK. She's been involved in multiple ground investigation and foundation design projects for the oil and gas industry, dealing with difficult ground conditions, including collapsible soils and expansive clays. More recently, she has been involved in potential impact assessment and foundation design for projects in the UK, such as Thames Tideway East and High Speed 2. In Chelsea to Battersea Pipeline project, she carried out settlement and impact assessments on the third-party assets, including input into the geotechnical baseline report. The floor is yours.
So thank you, Ivor. How is everyone this evening? Good? So I'm Andrew Hedgner. Thanks a lot for coming to the British Tunnelling Society event this evening. Tonight you're in for a real treat. We have an excellent presentation on the project, but before we kick off, just like to get a quick show of hands really. How many of you are contractors in the room? Okay. What about designers or consultants? Okay. Anyone from the client side, local authority? Okay, not so many. How many people haven't got anything else better to do on a Thursday night? Okay, me, that's it, yeah. Okay, so the topics we're going to cover are as follows. So I'm going to give an introduction and an overview of the project. Nick is going to talk about site management and site constraints. Ovi is going to talk about construction of the tunnel and the shafts. Veriuska is going to talk about geology, settlement and impact assessment. And I'm going to finish off with ground reinstatement in Battersea Park. So Cadent Gas. Who are Cadent? We're not a very well-known organisation, but we used to be part of National Grid. We were sold off last year to a big group of pension funds with lots of deep pockets, and now Cadent are the biggest gas distribution network in the UK. You You can see the geography we cover here. We've got 4 primary networks, and the project we're talking about here is in our North London network. Cadent has also partnered with 2 big construction outfits, Balfour BT looking after the west of the country, North West and West Mids networks, and Trio, which is a joint venture between Morrison Utility and Skanska. They're looking after East of Anglia and North London. So Balfour's and Trio, they primarily do gas mains replacements. In London in particular, Trio, they're replacing over 400 kilometres of gas mains each year. And that's in line with our 8-year RIO plan, our regulatory plan with Ofgem, and that's between 2013 and 2021. Cadent has over 130,000 pipes in the network, and we have 11 million customers. So the Chelsea to Battersea Tunnel forms part of our London gas mains replacement. So our strategic large diameter gas mains across London are deteriorating. We've had over 550, this stat's a little bit old, we've probably had more failures across the network on the medium pressure in the last 5 years. And Cadent are investing over £1 billion in the North London gas network in this 8-year RIO period, including asset health, major projects, above ground gas installations and so on. And we're replacing over 1,800 miles of gas mains across the 8-year RIO period. I'd just like to reflect on these pictures here a little bit, because working in utilities, as many of you will know, it's a thankless task. Nobody likes what we do. We close roads, we cause disruption from a traffic perspective, but people soon start complaining when they haven't got their gas supplies or water supplies. So, we can't do right for doing wrong. And these pictures here, these are, a good vintage, and when those gas mains were installed, people were on the side of the road cheering you on. Things are a lot different today. So a big part of Cadent's programme for the London mains replacement, we've got a project called the London MP Strategy. So that is to replace the strategic gas mains which run around Westminster, Kensington and Chelsea, to create a ring main, as you can see here, from Fulham up to Hyde Park, back through Knightsbridge. And we're also reinforcing the network south of the river, around Battersea and Vauxhall. We're also, we've replaced a lot of mains in the City of London and out towards Tower Hamlets along Commercial Road, all very heavily congested, high traffic areas, lots of disruption. It's really difficult work to do. And the Chelsea to Battersea Tunnel is highlighted here in the green area, or the green circle. So why do we need a tunnel under the Thames? So Cadent's got a small section of its gas network south of the river. That was a legacy hangover from when National Grid split up the networks and sold off to Southern Gas Networks, Northern Gas Networks and so on. We're reinforcing the network to facilitate the growth and regeneration and demand south of the river around Battersea and Nine Elms, where there's billions and billions of regeneration going on. Battersea Power Station, US Embassy, lots of residential, commercial, retail development going across south of the river, and they need more gas. The infrastructure there can't cope at present, so Cadent has an obligation to reinforce the network. So we undertook a study and we identified that, and I'll come on to this in a minute, but we couldn't get north to south river with the existing pipes that we had in place. So there's an existing bridge crossing, Grosvenor Bridge, adjacent to Chelsea Bridge, which we see here. Let's see if we get this to work here. So this is Chelsea Bridge. You see here, this is Grosvenor Bridge, this carries all of the southbound traffic out of Victoria Station, very busy railway bridge, and anyone who knows working on Network Rail infrastructure, it's an absolute nightmare to get possessions and all that kind of thing. So to undertake any gas work on a Network Rail site, so to speak, was out of the question. So that was discounted. We also looked at the possibility of utilising other existing bridges, but as you can see here, they're all Grade 2 listed structures, and the local authorities wouldn't permit new infrastructure going on their assets. We also determined as part of the feasibility study there were some old steam tunnels north to south of the river going to Battersea Power Station, but we couldn't guarantee the integrity and the condition of those tunnels, so we looked away from those as well. So we can't go over, that means we've got to go under. That one there. So Jacobs were commissioned back in 2012, I think it was, to look at a route corridor analysis between Fulham, where you see here, Fulham down here, that's where the high pressure gas comes in to this part of the network, and obviously Battersea, which is where ultimately we need to get the gas to. So the route corridor analysis identified a few potential options. It also identified Thames Tideway, that was obviously a big project that was planned, and it also identified Crossrail 2 potential, had a safeguarded corridor there, which we had to consider as part of our works. So from this feasibility study, we honed it down into 3 preferred options. So I'll just talk you through these in a little bit more detail. So option A, from Chelsea Embankment Gardens through to Carriage Drive North in Battersea Park. The site on the north on Chelsea Embankment Gardens, very slim, tight site, right next to Chelsea Embankment, TfL, strategic road, lots of traffic, difficulties with access and egress into site. Carriage Drive North, that's smack bang in the middle of Battersea Park. So wherever we came out of the tunnel, we'd have to do an open cut trench to Queenstown Road, which is the road that you see here. So again, open cut for a large diameter main through a well-established park, Grade 2 listed park, may I add, wouldn't have gone down very well. Option C, we found a Paxton Terrace, that was like a residential area where there was a big green in the middle, and a Battersea Power Station. The issues we found with option C were that basically that would compromise the redevelopment of Battersea Power Station, which obviously won't go down very well. So the option we landed on from a desktop-based study was option B, and that was a crossing from the Royal Chelsea Hospital, home of the Chelsea pensioners and the Chelsea Flower Show, and Battersea Park, the northeast corner by Chelsea Gate. So if we just look at this in a little bit more detail, it's been superimposed onto Google Maps. So you can see kind of the general environment. We've got Chelsea Bridge here in the middle. The alignment of the tunnel going north to south. You'll see further on in the presentation, some of the site constraints, particularly around Battersea Park, were quite challenging, which we needed to overcome. And the Royal Chelsea Hospital, as I've said, they host a national institution, which is the Chelsea Flower Show. It's been going on for over 100 years. The monarch attends every year, so factors like this we need to consider as part of the project. So in terms of the team structure, so Cadent and Trio, we've got a 8-year partnership in place, but Trio replace gas mains. They don't have any capability within their core business to undertake heavy civil engineering projects. So Trio went back into the parent company, to Skanska Civil Engineering, and we brought on board the project team, as you see here. So Mott MacDonald undertook all the design from the tunnelling, civil engineering, and the gas infrastructure as well. Skanska managed the shafts and tunnel construction with Barhale. Skanska also managed all the site kind of welfare, traffic, etc. And Barhale were appointed directly to Trio as the pipeline contractor as well. So looking at things from a desktop feasibility study is great, but when you have to actually go out there and start speaking to the stakeholders and actually saying, well, we want to come and do a dirty great big project in your nice manicured gardens, well, there's obviously some challenges around that. So for this project, there was significant stakeholder management, numerous consents and permissions that we had to secure, a big interface with Thames Tideway and the Chelsea foreshore, and programme constraints. The condition from the Royal Hospital and the Chelsea pensioners was, yeah, okay, fine, you can come on and do your work, but by no means can you affect the Chelsea Flower Show or the preceding events that happen over the summer. So again, these are the kind of things that we had to factor into our project. And these are just some of the handful of stakeholders that we had to engage with. Some came out of the woodwork, which we didn't even know that we had to engage with, but we drew on the experience of the wider project team, and we captured most of the stakeholders early on to engage with them. Cadent led the stakeholder engagement to ensure that there was a consistent message across all of the stakeholders. They understood the drivers for the project, why we needed to reinforce the Central London gas network, secure infrastructure and gas supplies for Londoners for the 21st century, and through developing relationships with those stakeholders, we managed to get them on side for what is quite a challenging engineering project. The RHS, to be honest, they got quite concerned about the fact that we wanted to undertake major engineering works in the grounds of the Royal Chelsea Hospital. So they were quite a big stakeholder that we needed to manage quite carefully. You can see here the red star on the screen. That's the location of the northern shaft, the launch shaft. That's right underneath one of their catering marquees. I don't know if any of you guys have been to the Royal Chelsea Flower Show, but it is, it's a very highbrow, prestigious horticultural event. So to have a great big dirty shaft underneath their catering marquee, they were quite concerned. So we did a lot of work with them to educate them and provide all the necessary structural information to demonstrate that the shaft and the location wouldn't have an undue effect on their marquee and the overall events programme as well. Another thing we had to do as part of convincing the RHS and the Chelsea pensioners is that if works didn't go according to plan, we had a contingency plan in place. So we had to build up different scenarios to say we could make safe the works, depending on what depth of the shaft that we went down to, cap it off, backfill, and hand the site back over for the event. So all of this went into the pre-planning and the consenting process to allow us to undertake the work. Another big interface we had was with Thames Tideway. So obviously, big, major £4.2 billion infrastructure project, development consent order, safeguarded corridor down the centre line of the River Thames. So Cadent had to agree through, they call it the guidelines for developers process. Tideway has that anyone wanting to build next to or near to their infrastructure has to go through quite a rigorous process where we provide all our settlement information, which we'll talk about in a little while. The design, you can see here it's all been coordinated in 3D in a nice microstation model. It looks quite impressive. I can't claim any credit for this. This was all down to Mott MacDonald, but these kind of 3D images were very useful in terms of the stakeholder engagement to demonstrate the engineering going into Cadent's project versus Tideways project. And I believe Cadent were also the first authority to get a successful approval and get a letter of no objection, a low no some of you may be familiar with, from Tideway for the works. Another benefit of coordination with Thames Tideway is the fact that we got to utilise their ground investigation information. So we had a massive programme and a commercial saving that we didn't have to mobilise our own GI, barges in the river and so on and so forth to undertake boreholes which fed into our design. And as luck would have it, SR1089 is bang where our shaft was going to be. And the finalised layout we have here. So we've got 30-metre deep shafts. We have a launch shaft which is 7.5 metres diameter. We have a 6-metre diameter reception shaft in Battersea Park. The pipe jack, 330 metres long, 1.8 metre diameter. At the time of feasibility, we weren't sure whether or not we could get land agreed on the south of the river for some gas infrastructure. So the tunnel was actually sized to accommodate 2 gas pipelines, which is why it's so big compared to the 18-inch pipeline that was eventually installed, but it was kind of over-designed for what we needed. And when we actually got permission that we could get the land, it was kind of past the point of no return in terms of the design, so we kept it at 1.8 metres diameter. And that's my first part over. I'll now hand you over to Nick to carry on.
Thanks, Andy. So my name is Nick McCrossan, and I actually work for McDonald, but last year, for 2017, I went to the dark side and joined Trio, who are the principal contractors for the project. And over the next 10-15 minutes, I'm just going to take you through what made this project much more complicated than a normal pipe jacking project. It was the constraints on both sides of the river, which added to the complexity of the project. So, as Andy said, the works occupy either side of the River Thames, so just north of Chelsea Bridge. We're in the grounds of the Royal Chelsea Hospital, and we're in the kind of north-eastern portion of Battersea Park. So it might not seem like the busiest place in central London, but the amount of additional development work going on in this area is quite staggering, because you've got Battersea Power Station development to the east of our site, but you've also got the Northern Line extension, which is feeding into that. You've got the Chelsea Barracks development, which is happening north of the river, and you've also got the Thames Tideway development, as Andy mentioned too. And in quite a small constrained area, you've got quite a lot of development, which obviously puts a lot of strain on the local transport network, a lot of the supply of resources and materials. So all these simultaneous and competing projects make things a little bit more difficult for us. So focusing purely on the Royal Chelsea Hospital site, which was our launch shaft, I'll go through some of the constraints. So the biggest one is you've got Tideway. So they're building an offline shaft just adjacent to the Bull Ring Gate at the Royal Chelsea Hospital, and they've also got an interception tunnel which is running from the Ranelagh Gardens into the shaft. So we had to coordinate all our works with them when they started on site last year. You've got the TfL Red Route on the Chelsea Embankment, so this is one of the major transport veins of London, which tends to get quite congested, making it difficult to get materials in and out. We've got 2 key Thames water assets which run underneath the site. These are the Ranelagh sewers. So for the duration of the works, we had to make sure that these were protected, and we were measuring any kind of impact to them, which I think Verushka is going to go through in her section. The hospital itself, if you're not familiar, is a care and retirement home for over 300 ex-military personnel. So obviously we have to be very cognizant of the impacts that we have on them as a community. So especially when we went to 24-hour working for the tunnelling portion, we had to make sure that we were minimising any visual and noise impacts as a result of our works. And the ground, as Andy stated, during the summer it's quite busy with events such as the Royal Chelsea Flower Show, but it also hosts things like the Masterpiece London Art Fair, and the Longines Master Equestrian Champions Tour. I think I've messed that one completely up. But also, during the winter months when we were on the site, the grounds are open to the public, they're open to schools, they use them for PE lessons, and also they let the grounds out for filming. So while we were here, they were filming the new Winnie the Pooh film, so you have to share the rest of the grounds with other stakeholders as well. So what was actually quite a pleasant surprise was you would think that the hospital at our level would be quite stuffy and wouldn't be very flexible, but the hospital during the duration of the works were absolutely fantastic, and the residents themselves were very interested in what was going on, because you had ex-miners and ex-engineers who were wanting to come down, and they were offering advice and they wanted to see behind the hoardings, and it was really good to actually get them out onto the site to see the works going on. As Andy mentioned, our biggest interface was with Thames Tideway Tunnel, so what was quite important is you don't compete with another project, you have to help each other deliver it. So we had to make certain accommodations in the work we were carrying out at Chelsea to make sure that Tideway can complete their programme of works as well. So that was one of our major considerations. And taking account of the summer events, that had a major impact on our programme. For about 5 months of the year, Chelsea was out of bounds, we couldn't carry out any work. So we had a very short window in which we were able to construct a launch shaft. Then in the 2017 summer events, we had to go over to the other side of the river, mobilise, build a reception shaft, and then we had a very small window last winter in which we could start the tunnelling and get the pipeline installed and tested and commissioned. So it's quite a intense and constrained programme we had to work to. So we had to go from here, a fully mobilised site at Royal Chelsea Hospital with our cabins, our exposed shaft, all our plant materials, to a state where it was fit to hand over to the hospital for their summer events. So we installed a prefabricated cover slab made up of 12 planks, covered it over, backfilled the shaft and the ground and handed it over to the hospital. And I know what you're thinking, you think that looks absolutely horrible. You see you've decimated the Royal Hospital's grounds. But what's quite interesting is after the end of the flower show, that's the state that the hospital's left in. The flower show, there's not a blade of grass to be seen when they leave the flower show. And the hospital got an incredible team of landscapers and gardeners, so they're able to, in the space of a matter of weeks, turn it from like a brownfield site to that. And looking back into the history of the hospital was opened in 1692. And for about 200 years before the Chelsea Embankment was built, the river used to go right up to the edge of the gardens. So you would have jetties and you'd have slipways available for marine transport to use as an entrance to the hospital. And then in 1874, when the Chelsea Embankment was built, the grounds themselves were, the gardens were extended, the jetties were lost, until on our 4th day of construction we managed to find one in the shaft. So we managed to find it was about 500 metres, 500 mil of a masonry jetty structure, supported by these fantastic semicircular timber piles. We found about 14 of them in the footprint of the shaft, and they had these fantastic steel cutting edge on them. You may not be able to see it for the mud. But these were left over from when the hostel was constructed originally as well. Focusing over the Battersea, over the other side was a bit more challenging. The site itself is located in the northeastern portion of the park. This isn't a Thames walkway, but this is a walkway that's required to get from the park itself into the Battersea Power Station development, and that was required to be remain open for the duration of the works. As with anything in this area, everything seems to be Grade 2 listed, so with these Grade 2 listed wrought iron and masonry gates through which all our construction traffic had to go, so all our materials, all our concrete, everything had to come through these gates. And we also had a river wall which was located just less than 10 metres away from our shaft, which was a major concern, and Vrishka's going to talk a little bit more about that, about how we managed it. On the site itself, the topography was quite variable, and we had, as you can see in the lot on our stop, we had a tree which was causing us a little bit of bother. It was quite a considerable tree, about 1 metre diameter, and it forced us to have to place the shaft in the middle of the footpath, which you can see here. Very close to the river wall, and also quite close to where the footpath was running along the site. And due to topography, we had about 1,100 metres squared of site available to us. But due to all these constraints, we can only use about 44% of it. So the biggest constraints at this site were the removal and storage of muck. So the actual the progress of the construction at Battersea was linked to how much material we could store on site and get away as quickly as possible. Also the storage of our segments and our other materials for building the shaft, and plant movements moving in and out of the shaft in quite a busy pedestrian area are key as well. And our traffic movements were our biggest hazard on the site. So you can see here from the left to right, there's quite a variable topography on the site. And I think Barhill done a fantastic job of creating a safe working environment. So they cast this retaining wall which was used to create a stable platform, but also you can see it left enough space for the footpath to be open for our pedestrians or for our cyclists. It was backfilled. They created some safe working platforms for the plant. And also they've done a good job at not interfering with the tree canopies as well. So our friends at Battersea Park were quite happy about that. And then we come to Amanda. So Amanda was an Uncle Iseki, an Iseki Uncle Mo machine. And instead of going to local schools to name the TBM, we actually went to the Chelsea pensioners, and we opened up a ballot for them to be able to name the TBM in recognition of some of the staff that work up at the hospital. And the director of the infirmary, Amanda Lord, was chosen as the recipient, and I think it must be quite a surreal moment to be taken into a meeting room and told we're going to name a big dirty machine after you. But we had a fantastic event on the 6th of October last year where we invited the Chelsea pensioners and the Friends of Battersea Park and a few other stakeholders to the site. It gave them an opportunity to learn about how we construct projects like this. It gave them a chance to ask questions and also see around the site and interact with the machine itself. And it was a great photo opportunity to get the Chelsea pensioners in their red jackets and their PPE next to our machine. So I hope I've been able to give you an overview about what made this project more complicated than a standard pipe jacking project. And I'm going to hand over to Ovi now to take you through the construction methodology.
Good evening all. My name is Ovi Frunze, and I'm going to introduce the core elements of my presentation. I'm going to describe the construction of the shafts and the tunnels, and focusing on the effect of slurry management and lubrication to the predicted jacking loads. At the launch site in Chelsea, the main constraints was that the works had to be delivered around RHS Chelsea Flower Show, as such that we had to pick up a method and plant that will enable us to mobilize and demobilize quickly to leave a place for the prestigious event to take place. At Battersea, there was steep topography. Site area was a lot smaller, and proximity to the Chelsea Bridge and river wall, and also there was some mature trees in site. So with this in mind, we had to reduce the size of the shaft to 6 meters. That was the smallest size to enable us to take the TBM out. And also we had to integrate the construction of the collar and the working platform so that, and also leave a pedestrian footpath within that proximity. So in terms of geology, we had around 2 to 5 meters of made ground at the two shafts, which was underlaid by around 4 meters of water-bearing strata made of alluvium and River Thames deposits, which was underlaid by 35-meter deep clay layer. So we needed to find a solution to construct the structure through the water-bearing layers and deep into the clay. So given the considering the constraints presented, we decided that the best approach would be to construct the caisson method, going to the water-bearing strata and then switch to underpin method once we are in good clay. So for the caisson shafts, they were built of segmental rings bolted on the top and jacked with jacking gallows, which were anchored into a collar. The structure was underlaid by a catenage, which was both shearing the ground and creating a 50 millimeter annulus, which was filled with the lubricant. This lubricant maintained active pressure on the face, on the excavation face, and also reduced the steel friction. Once the structure was down into clay, we pumped the water out because this structure was built submerged. And once we pumped the water out, we replaced the lubricant with grout, and we used a special ring to enable us transition from the caisson method to underpin method. Short animation showing how we built the shaft. So we built a catenage, a choker ring on top, and then the collar was constructed with a 50 millimeter space between collar and the structure, which was used for lubrication, to insert lubrication, and also used to control the structure verticality by introducing steel shims. And together with the jacking gallows, we managed to project to construct the shaft on a vertical trajectory. So that's how we built the shaft, caisson, adding more rings, all done on the top, and then through the water layers. Once in clay, pump the water out, replace the catenage. We built the underpin by excavating 1.2 meter advances. Then a ring was placed, grouted, and then we finished at formation by constructing a under-rim base, which together with bolting the collar to the shaft, enable us to balance the buoyancy of the structure. It's quite difficult to grout caisson shafts properly. So additional to the traditional methods of using pressure gauges mounted on the grout lines, we use a thermal imaging camera, which enabled us to control where we put in grout and enable us to treat sections of the shaft that show no grout present. With this, we managed to control the settlement within the predicted values. Due to the depth of the structure, which is 30 meter deep, we had to strengthen the segmental liner, and we built a secondary lining. But before doing that, we thought we need to do some tunneling works as well, enabling building a portal, building a thrust wall. So let's optimize the design and construct all the structure in one, which we did, and saved us some of the program. We measured the construction rate for the tunnel, for the shafts, and we established that the underpin method was slightly faster, which we kind of knew, and that was one of the reasons why we choose to switch to this method. However, heavily reliant on good ground conditions and resulting in slightly more settlement. One of the other advantages of the caisson shaft was that most of the structure was built at ground level without people having to work in confined space, so the structure jacked down. Second part of my presentation will be around the tunnel construction. So the corridor available to us, located between existing structure and Thames Tideway tunnels to be constructed, was in good clay, which was ideal for an open face TBM. However, drift hollows near Chelsea Bridge determined us to take a safer approach and go for a slurry TBM, closed face called Isaac Ankle Mall. This was able to deal with a range of ground conditions, also able to crush boulders up to 500 millimeters. The slurry was formed by mixing water into the ground by the rotary head, movement of the cutter head, and had both effect on maintaining excavation face pressure and also conveying the tunnel risings to the ground level where they were treated. The TBM trajectory was controlled by a pipe laser, which was fitted in the drive shaft, and the beam of this laser projected on the TBM, and TBM driver could make some adjustments using the steering joint available within the TBM. We set up a flying factory at the drive shaft where all the tunnel services were pre-installed in the jacking pipes, hence enable us to reduce the work in the confined space and increase the output of the tunnel construction. The lubrication was inserted in the overbreak through pipe outlets, which were uniform distributed around the tunnel. The pit bottom at the launch shaft, 7.5 meter size, quite congested. All the pipes and operational valves have to be placed such a way that we can operate them quite quickly. We used a 600-ton jacking rig, and due to the space constraints, we had to use a jacking spacer, which enabled us to extend the stroke of this jacking rig and push the tunnel so that we can make room for another pipe. We have used a gland plate, which was a composite between a steel plate and a rubber gasket, which enable us to maintain the lubrication pressurized around the tunnel, hence reducing the friction. One of the features of the microtunneling system that we used was that it was largely automated. So the TBM driver and the team built the tunnel from ground level with little interventions in the confined space, such as adding a new pipe. The controls of the TBM, all the indicators on the top side of the control panel, the driver could make adjustments in steering and slurry control, and then the lubrication control displayed at the bottom of the control panel. Another quick animation about the pipe jack and how we did it, with the pipe lowering into the shaft, the pit bottom. So one of the problems we had was that the predicted total jacking load was around 1,200 tons. So this was exceeding the capacity of both the thrust wall and the capacity of the pipes. So we had to find out a solution of how to distribute that load, and we introduced two interjacks. So that enable us to construct the tunnel. The downside of the introducing interjack is that it increases the construction time of the tunnel, and it's going to have an effect on the total jacking load ultimately. So we monitored the jacking forces, and we knew that the jacking load will increase with the tunnel length and with time. And lubrication was key to ensure that the clay distension is retarded and result in less friction and less thrust required. The thrust wall load, which was in the blue line, was measured versus the predicted load. And as a result of this good lubrication, the jacking force was less than predicted. This enabled us to utilize later the interjack, which was introduced, the interjack 1 introduced at pipe 20. So that was not required until pipe 97, which had quite a good effect on the tunnel output. We monitor the earth and face pressure, establishing that high value as we left the drive shaft, and lower earth pressure underneath River Thames. In terms of slurry separation plant, it's an important process associated with the use of slurry. TBM is the means by which the slurry is produced, treated, and managed. The slurry processing rate is instrumental to the tunnel output and also to the waste volume. the separation plant is configured by the size of the tunnel and the ground expected. So we had the GBR information. We took some additional samples at the tunnel horizon to enable to consolidate that GBR information and to fine-tune the plant and the polymers that we're going to use to separate the slurry. How does it work? So the dirty water coming from the TBM goes to a clay ball pod where particles above 20 milliliters are segregated out. Then the slurry travels down to a descending unit, removing 6 millimeter particles through shaking beds, and then through conical shape hydrocyclones where the centripetal force is removing the solids to one side, and the slurry goes down to the dirty water tank. The last process is in the centrifuge, where we added a flocculant to enable all the suspended solids to attract, forming clusters, which were spun by a fast motor, and particles removed out, and then the clean water was pushed back into the TBM. After 330 meters and some fine engineering, the TBM was retrieved within the portal tolerance, despite engineers saying that it's too small. So in conclusion, we installed the pipeline after the construction of the tunnel and the shafts, and the whole project was recognized for minimum disturbance. Key was the fact that we automated quite a lot of the process, trying to work less in confined spaces, and lubrication and slurry was key in achieving 330 meters in 24 days. I would like to hand over to Verushka for the last part. Thank you.
Okay, my name is Verushka Ortiz. You did a very good job with my name, it's not easy. And I was involved in the estimation of the settlements and the impact assessment. So, because this project was carried out in an urban area, we had to ensure that third-party assets were not going to be affected by the construction works. And therefore, we had to carry out an impact assessment. So, the first stage of the impact assessment is estimating the 1 millimeter settlement contours, or the settlement contours in general. And what happened here is that we can see here in red, that's our 1 millimeter settlement contour. So all the assets that are within this area here, we expect that we have 1 millimeter or more of settlement, and therefore all these assets have to be analyzed. In our area, we had assets as water mains, we had gas mains, we had electricity and telecom cables, we had the Chelsea Embankment river wall here, which is a grade 2 structure. And then we also had some assets that we had to pay particular attention, like for example the Ranelagh sewer, which is a Victorian brick sewer. And also, as it's been mentioned, the Thames Tideway Central project, and for this one, because of the interaction of our projects, we had to carry out a separate impact assessment, accounting for the combined effect of both projects. And then also we had to pay particular attention to the Battersea River Wall, which after the condition survey, it was classified or categorized as grade 4, under the environmental agency grade as, well, the rating, I don't know how to call it, which essentially what it says is that the river wall was in poor condition, and we found that there were cracks from 5 millimeters to 15 millimeters. There were some blocks missing, so it was in poor condition. The ground conditions were typical of London geology, so it was made ground, overlying alluvium overlying river terrace deposits overlying London clay. We found groundwater in the superficial deposits, but not the watering was required for our project. So the top of the London clay here was found around 8 meters below ground level. And I just want to stress that during the construction, we tried to use as much caisson or excavate by caisson as much as we could. And for the Chelsea shaft in this area, we excavate around 22 meters by caisson. And then when we arrived to the top of the to the London clay A3, which is a stiffer material, then we changed to underpinning. In the Battersea, for the Battersea shaft, it was a similar ground conditions, just that in this case the superficials were a bit thicker, so there were about 13.5 meters. And in this case, the caisson was used until around 17, 18 meters. Some particularities of this job is that during the excavation in London clay, we found big claystones of up to 500 millimeters. So yeah, this was something that was also picked during the GBR. Actually, we found really big claystones here. Okay, so for the impact assessment, how do we estimate our settlements? So how do we get our expected settlements? So at the moment, the methodologies to estimate the settlements are empirical. So this means that all this data from these projects are still feeding these methodologies. In the case of shafts, we use the methodology of New and Bowers from 1994. What this says is that, let's say this is our shaft, and what this methodology suggests is that the settlements around the shaft are going to follow a parabolic envelope, and the maximum settlement is going to be related, which we see also here, will be related to the depth of the excavation. And according to New and Bowers, our maximum settlements are going to be around 0.06%. Regarding the width of the zone of influence, then New and Bowers suggests that it's going to be equal to the depth of the shaft. And then we can see here also representation. In terms of the tunneling, we assume an inverted Gaussian distribution. And in this case, the maximum settlement here depends on the volume loss, but the volume loss also depends on the construction methodology. So for the estimation of these settlements, it was particularly challenging to find volume losses for pipe jacking, and we found that there is not much data available. So we assume a volume loss of 2% and a K value of 0.5%, which is the coefficient that characterizes the width of the trough. Okay, after carrying out our impact assessment, we found negligible impact for all our assets, so we didn't require any mitigation measures. However, to be sure again that our predictions were going to match the reality during the construction, we planned a monitoring campaign. Our monitoring campaign was mainly based on surface leveling points, which are these red dots, and with this we were going to measure the settlements around the shaft. You can see here, this is the Chelsea shaft, this is the Battersea shaft, and for the river walls, because they are sensitive structures, we had a dual system. We had an automated system based on till meters and hydrostatic leveling points, but we also supported the automated system with manual measurements with prisms. And also we got a certain level of redundancy. During the installation of our monitoring system, we had to be in close collaboration with Tideway Centra because, as you can see in this picture, our instruments were right beside theirs. Additional to that, we installed 9 monitoring manholes. 6 of them were along the Chelsea Embankment, and this also required close coordination and communication with TfL and with Taiwan Central Project. Okay, so now we have the results and what we got from our recordings, our measurements. So what we're seeing here is our settlements and how they evolve during time and during the construction. So what we see here, and the first thing that we notice is that we have our settlements here during the 22 meters of caisson. This is for the Chelsea shaft, I'm sorry, I didn't mention it. So we saw our settlements during the 22 meters of caisson, but as soon as we changed to underpinning, then the rate of settlement increased and almost doubled. And what we saw after this is that after the routing of the base slab, the settlement also seemed to stabilize. Something similar to that we also have it here in the Battersea shaft. So we have our caisson settlements, and when we switch to underpinning, then the rate of settlements increase. And again, after pouring the base slab, settlement seems to stabilize. So what we can conclude from these measurements is that the methodology of construction actually plays a part in the magnitude of our settlements. In terms of the magnitude of our settlements, what we're seeing here is this is a normalized distance from the shaft, and these are our normalized settlements. For the Chelsea shaft, we can see in this grid line is our predictions, and these are our measurements. Actually, what we found here is that our maximum settlements were smaller than what we predicted. So instead of the 0.6%, we're actually around 0.4%. However, the width of our zone of influence was around 1.9 times the excavation depth. So it was larger. For the Battersea shafts, again, something similar. This is our prediction. And here the settlements were a bit bigger than for the Chelsea shaft, but again, they were smaller than our predictions. The maximum settlements were around 0.05%, and the zone of influence was around 1.9 times the depth of our shaft. And because both of the shafts were of similar diameter, we couldn't really see what was the influence of the diameter in the settlements. So some research from 2017 and from this year has supported the relationship between the methodology of construction and the settlements. So essentially what this research says or suggests is that, let's say you have, when you construct your shaft, if you install first your lining and then you excavate, then your settlement seems to be or tend to be smaller. But then and this will be, for example, the case for diaphragm walls or bore piles. So first you start your lining and then you excavate. So that will bring smaller settlements. Then instead, for example, if you excavate ahead and then you install your lining, which will be the case for underpinning or for SCL, then this data suggests that the settlements are actually larger. In the case of the caisson, it's kind of an intermediate case because it will depend on how the construction is carried out. So let's see more or less how our data correlates with this research from last year and this year. What we're seeing here, these two graphs are from a technical note that new presented in 2017. So this data is from underpinning plus SCL, and we can see, and the difference between this and the original Neuenbauer's approach is that a generic equation is suggested. So now this accounts for a wider zone of influence, and immediately we can see that with a wider zone of influence, our measurements correlate better. However, again, we can see that our maximum settlements seem to be smaller than the ones suggested by this method. In the case, we have here some data from Faustin, and this is for diaphragm walls and bore piles. And we can see that now our settlement seems to be larger. So it doesn't quite fit again the data presented. But then now we have Cason methodology. The thing with this data is that during the excavation of this shaft, it was used solely Cason. So all this shaft of the shaft was excavated by Cason. And then we can see that in the Chelsea area, for the Chelsea shaft, our data match or is very much in agreement with this data. And let's remember that this was around 70% of the Chelsea shaft was excavated by Cason. So I think it makes sense. But in the Battersea area, though, we still see that our maximum settlements are very larger. Something that I forgot to mention is that all this data also accounts for larger or wider zone of influence, and that's also something that we observe. And finally, you can see a mixed methodology. So in these cases, during the superficials, they use Cason, and then when they arrive at stiffer material, or to London clay, because it wasn't London clay, they use SCL. And then we can see that this is actually what it fits better our measurements. And now we go with the tunneling. In the case of the tunneling, we conclude one thing. First is that our settlements follow an inverted Gaussian distribution, so that was good. Then we back calculate some volume losses, and we found that the volume losses were for the Chelsea shaft from 1.2% to 2.5% locally, very close to the long shaft. We also saw a set of measurements that were very, very small, and these were close to the Chelsea Embankment river wall. So we think that this might be due to the stiffening effect of the river wall. And then for the Battersea area, for the south side of the tunneling, then we see that the measurements match quite well the 2% that we estimate. In terms of the river walls, for the Chelsea River wall, we visually perceive no impact, so negligible. In terms of the Battersea River wall, we have here a longitudinal section and a transverse section. All the data measured by the hydrostatic leveling cells match our PLPs, but in the case of the till meters, we couldn't really, or we assessed very negligible impact in the longitudinal section, and in the transverse section, we only notice a little bit of movement towards the shaft during the underpinning, but it was really negligible, and the same happened for the tunneling, very negligible impact. So the three things that we concluded from our monitoring campaign and our impact assessment is that our predictions were reasonable, and the movements during construction were small, and they didn't cause any impact. But this is only possible when you have a good control during the construction. The second thing that we also notice is that the importance of the methodology of construction. Actually, the methodology of construction for shafts plays a part in the magnitude of the settlements that you will obtain. And now also the third thing that we concluded is that for pipe jacking, now we have some levels or some numbers of volume losses that for our case was 1.2% and maximum of 2.5% locally.
Just a final few slides now, guys, about how we've reinstated Battersea Park. So you'll have noticed from earlier pictures the area in Battersea Park where we're working was less than well kept, let's say, by the park. overgrown with vegetation. Also, the park had some concerns about security in this area. They've got a CCTV network and they didn't have coverage in this part of the park. So as part of the agreement to the construction license that we had with the park, we installed a new CCTV camera just off to the side of the picture on the left here. After all the civil works were complete, Bar Hill reinstated the site back to its original level. We painted all the railings, put everything back, nice layer of topsoil, did a really good job, in fact, and resurfaced all the area. You wouldn't be able to tell that we'd done anything, to be honest. But what Cadent, as part of a kind of conscientious company, did as part of the discussions with the park is we agreed to re-landscape as well. So the landscapers have actually started on site this week. They'll be there for a couple of weeks if you're in that neck of the woods, so pop by and say hello. The planting scheme, we won't see much benefit between now and the spring, but in the spring, hopefully, if the plants don't die off over winter, that is, will bloom into a lovely, colourful area of the park, and it'll give some betterment back to Londoners and to the users of Battersea Park. So, just a few key facts about the project. So £17.5 million, same value as the most expensive British car in history, the Aston Martin DBR1. The project overall, 17 months to complete. The civil engineering works, that is, and the pipeline installation in the tunnel between November 16 and March 18. Amanda is named after Amanda Lord, infirmary manager of the hospital. 330 metres, the tunnel's longer than the Shard, is tall. We excavated over 4,500 cubic metres of material, which is equivalent of 30 double-decker buses, and we had 0 lost time incidents during the project, which is a really great achievement. So we've now got a short project video, which will come on now. Makes it look so easy, doesn't it? So that's the end of the presentation. Thank you guys for listening. We'll take any questions now.
What a fantastic job. I think we must have a stack of questions. Who's going to be the first? Name and organisation, please. There's a microphone coming down to you, if you could wait for it, please.
Yeah, so I'm John Harris from Biohelp Construction, actually. So I've just got a question concerning the lubrication jacket on the caisson shaft. You indicated in the slides that you changed from caisson to underpinning roundabout, looked like it was around about 15 or 16 metres below ground. And I couldn't quite get from the show where you transitioned from sedimentary to clay. And I wondered just what your what your shaft lubrication regime was. I mean, did you just top feed with your lubricant all the way down to the point where you took the cutting edge off, or did you have to do something positive, like injecting it from above the cutting edge or further down the shaft?
Okay, so when we reached the clay layer, we went a few more meters, and then we pumped the water out. At that stage, we replaced the lubricant from the bottom up by pressurizing grout before we removed the cutting edge. So the grout was effectively pushed outside around the collar, and grout replacing the lubricant this way. And with the thermal imaging, we went ring by ring to ensure that the grout is uniformly displaced around the segment.
Well, my question is less to do with grout, but actually the actual lubricant. Were you just feeding lubricant into the jacket from the surface all the way down?
Yeah.
And that worked satisfactorily?
Yes.
Yeah. Thanks for that.
Back there.
Peter Townsend from Mott-Mac. What happened to the shaft and the tunnel once you installed the pipe? Did you flood the tunnel, and did you backfill the shaft?
I can answer this as well. So we backfilled both the tunnel and the shaft once we installed the pipeline. So the tunnel was backfilled with the bentonite mix, and the shafts filled with sand.
And from a kind of gas engineering perspective, having an asset in an open area creates a maintenance liability. So from a operational perspective, it was better for Cadent to backfill everything, so we didn't have that ongoing long-term liability, putting people down in confined spaces with potential gaseous environment as well.
Can I just ask a second question then? Did you use cathodic protection on the pipe?
Yes, we did, yes.
Thank you.
Another question. Andy Sindel, you got a question back there? I know there was no SCL in there, but...
Well, Siggy's mentioned it, I must ask something. I'm curious, you've got an open cut, I think, going from the Battersea shaft towards the dog's home.
Yes.
As you've already got a tunnelling machine in the ground, why don't you keep going and save all the disturbance in the area?
Yeah, very good question. I think the cost of extending the tunnel towards the dog's home was prohibitively expensive compared to open cut. So that's the decision that we made. We did look at it, but not for very long. So.
Steve Parker, for name and affiliation, Steve.
Thank you. A question on the monitoring of the wall. It seemed like there was very small movement. Did you not, in fact, find that the tidal influence would have been much bigger than the movements you actually detected? And on your graphs, it didn't show anything about tidal movement.
Well, essentially what we only recorded was seasonal and tidal movements. Maybe because of the scale during the tunneling, it was a very, very small settlement. Also because in the very small movements were in the transverse section, but in the longitudinal section where we showed two graphs where you can actually see all the tidal movements. But as you said, it was more the seasonal and the tidal record like settlements and movements than actually the one from our project.
So the tidal movement was more than the tidal
Yeah,
movement.
yeah.
Frontier.
Thank you. David Fawcett. Do you think that by using a slightly increased face pressure, you could have got less settlement?
Sorry, can you say again? If we use...
Well, you've got 2% settlement, 2% face loss.
Yeah.
And do you think that by using a higher face pressure, you could have achieved a lower face loss?
Could, yeah, maybe.
Or do you just think the 2% didn't matter? It probably didn't.
Yeah.
Well, with the 2% occurred, it was within the grounds of the Chelsea Hospital, so it wasn't a major issue. If it had been closer to one of the river walls, it would have been.
Yeah, I think also what we tend to compare pipe jacking with bigger TBMs and normal TBMs, and actually we have found that for pipe jacking, historically volume losses are higher. So I think, well, our intention here was open the discussion and see, precisely that, analyze what could have been happened, what can be improved, and yeah. But.
Hello, good evening. Kim West from Arab. The slurry machine seemed to cruise on through. In terms of the cleaning system for the slurry, had it been used before in London Clay? Can you tell us a little bit more about teething problems with the slurry cleaning?
Well, like I said, we looked at the particle distribution when we done the samples at the tunnel horizons. We compared with GBR. When we set out the slurry equipment, we had a pod for all the particles. So we took some samples and we analyzed how quickly can we get rid of the suspended solids from the fluid. That enabled us to fine-tune the polymers that ultimately removed all the small particles from the fluid. So that was the gist of us taking samples before we start tunneling. So by the time we got to do the tunneling, we had an idea what we need to use to clear the slurry effectively.
And so you had no surprises?
No.
Frontier now.
Thank you. John Davis, GCG. Two questions, if I may, Ava, completely different ones. I have a bit of a research interest in Driftfield Hollows. You've mentioned them in passing. Did you find any? And if how would you have noticed?
Well, we monitored the arisings from the TBM, and also TBM was has a feature of having a microphone in it, and then if you come across any granular material, that will notify the TBM driver. So within his reports, we didn't find anything but good clay.
And the second one's completely different. The other interest I have is GBRs. GBRs you've mentioned in passing a few times. And it's always seemed to me to be, when you've mentioned them, you've mentioned in the context of some design decision. First of all, so do you really mean a geotechnical baseline report in a commercial sense? Or do you mean a sort of interpretive report? And if you were using GBRs for design, it strikes me that they must have been quite reasonable and realistic in relation to what we would call engineering judgment view of the ground. Is that fair? It's not a question, is it? What was the GBR like in terms of its relationship to what we would normally expect in London Clay?
Well, the information from the baseline was fairly accurate, although inclusive of a lot of possibilities. But where we're supposed to have the ground water and the composition of the ground was in line with that. So there was some obstructions at the beginning with the archaeological stuff, but we expected that, so it's quite good.
Have we got any more? Yeah, there he is. Oh, big
Andrew Smith, retired. I was unclear why you changed to underpinning and the shaft construction. Didn't explain. Was that just a policy decision? I mean, to me, it would have been better to go to the bottom, or was there some reason why you couldn't?
Yeah, so there's few reasons. With there's a feasibility and cost of construction. We knew that underpin method is going to be a cheaper method. In terms of depth and reach, we could only reach so far with the caisson by excavating from the top. Now, looking back on the data and the settlement analysis, I think caisson is a better option, but depending on the depth of the structure, obviously. And the other downside is deeper you go with the caisson, more complicated is to remove the lubricant and pressurize the grout and push all the lubricant out.
One more here.
David Chu from GCG. If I understood correctly, you said the zone of influence was actually larger than you initially thought. Did that give any concerns to the asset owners, and did you have to revise your impact assessment with the monitoring results?
Actually, I think, well, yes, it's something to consider because we've been finding new data that actually accounts for a wider zone of influence. However, in that area of extended zone of influence, the settlements tend to be minimal. So I think it was, of course, a case-to-case, like in every project you need to evaluate the special conditions, but I think actually in that area, settlements will probably produce a negligible impact in the assets.
To add to that, we had a emergency plan in place, so if the thresholds were breached, we'd invoke contingencies with the other utilities. Thames Water in particular were a concern with the bricks that you saw earlier.
So, any more, or? Yep, Jim.
Yeah, Jim Worthington, formerly with Balfour Beatty on the Tideway project. You've mentioned the interface with Tideway, and your tunnel has been constructed above the main tunnel, which is still to go through. I just wondered what influence settlement of that main tunnel may have had on the design of your tunnel.
Well, we carry out two separate impact assessments, and we carry out so the combined impact assessment for third-party assets with Tideway and our project, and actually the Tideway project settlements were like massively larger, so actually that made no difference for us. And also we carry out a second impact assessment of the Tideway project in our tunnel, and again we found that it was also negligible impact in our tunnel, so from that sense also we were covered, so it wasn't any difference.
Thank you.
The other bonus in completing our tunnel ahead of Tideway is they've got to work around us now, rather the other way around, which is always nice.
Okay, so we'll draw the questions to a close now, I think, and we've two reasons to thank our speakers tonight. And one is for obviously an excellent presentation on a fantastic job. The second reason is that the team is sponsoring the bar tonight. So perhaps if we could thank them in the usual way.